Welcome everyone. In this video I'm going to continue the previous video's experiment. To see what is my previous video was about, please check it. In that corner there should be a link or something, but I will briefly summarize everything. So we are using this DC-DC buck converter. You can see that this is this SZBK07 DC-DC converter. So it can accept an input voltage between 6 to 40 volts, and it will provide 1.2 to 36 volts on the output, and it can provide maximum 20 amperes when you can cool it actively, but otherwise it should be used at around 15 amperes according to the manufacturer's description. So as you can see, there are two potentiometers on this. These kind of trimmer potentiometers. So these screws are multi-turn screws, 100 kilo ohms value, and the CC is used to control the current, and the CV is used to control the voltage on the output. So the goal was to somehow override this system and convert this thing into a voltage controlled voltage control. And by that I mean that I want to control this digitally, and by that I mean that, for example, as you can see it here, I want to have a digital potentiometer and control the output voltage of this thing. But if we want to use that, we are limited in a narrower voltage range, 0 to 5 volts. And that can be our controlling voltage. And the problem here is that we have the output pin, the positive pin, and that directly goes to the potentiometer, which is controlling the voltage or giving the feedback signal to the feedback pin of the buck controller. And that's a big issue, because if you are using some voltages on the output which are higher than 5 volts, and you would incorporate your digital potentiometer here directly, then you would kill the digital potentiometer, because the maximum voltage which can be used with it is 5.5 volts. So you cannot do a direct exchange like you would exchange the potentiometer, this blue box, into this, which I already did actually, and this works. And you can see it here as well. But you cannot exchange this to a digital potentiometer, or not to that type that I use. So we had to figure out another way. And then that was the previous video that I figured out that I desoldered this potentiometer here. So that's the guy that you see here in the corner. And then I figured out how it is connected. So the positive output of the DC-DC converter goes into the pin number 1. So that's what you see here as the blue wire. And then we go to the red wire, and that goes back to here. But also we have a 10K potentiometer here. And we should connect the 5 volt to this side, or the 0 to 5 volt voltage range. And that will be realized with this potentiometer here. So what we should do is we should digitally switch the digital potentiometer, and that will be realized with a rotary encoder, and that will give us the control voltage for this. But there is a trick here. So we still have the opportunity to set the voltage by using this potentiometer. So regardless of the connection of this, so let's say we are not connecting this part with the resistor, we are still able to set this potentiometer to a certain value, and then we can control the output voltage. And there is let's call it slack in this potentiometer, and by that I mean that if I start to turn it from 0 to the maximum value, then it will saturate earlier than the mechanical limit of the potentiometer. So first of all, we have to find that point, like mechanically, where further increasing the angle of rotation will not change anything in the output voltage. And after that we can use the voltage on this pin or on this terminal to control this DC-DC converter. So what we will do here is that here I have an STM32 circuit, but you can use an Arduino instead of this. The code will be compatible with that as well. And that STM32 is connected to a rotary encoder. So this will allow us to change the bit between 0 and 255, which is written on the input of the potentiometer. And then here we will see everything on a LCD. And here we have this MCP 41100 digital potentiometer. So it's an 8-bit potentiometer. As I said, we will set the bits between 0 to 255, and that will provide an output voltage between 0 and 5 volts. So I will quickly show you how this works, and at the end of the video I will also show you the source code as well. So this connection is not the best, so I will try to fix it in some way. So now it's good. So the screen is on, and you can see the display that we have a potentiometer level, and that is basically just a number in bits, and we have the voltage, which is just a calculated value. And by that I mean that this thing should know that if the bit is, let's say, 0, then we have 0 voltage, and if it's 255 we have 5 volts. So then it just divides everything based on the value of the bit. So I hope that this is visible. So we are at 0 and we have roughly 0 output voltage. And now I just change it by 1 bit. And you can see that 0.02 volts, so 20 millivolts, and here we have 31 millivolts. The 5 volt rail is not exactly 5 volt here, therefore the mathematical operation inside the STM32 is not precise, because here what I do is that the number of the bit is multiplied by 5 and divided by 256. And if the voltage on the 5 volt rail is not exactly 5 volt, then this division and multiplication will not be exactly the value which we read here. So now, yeah, we just go to some value. But you can see that it's increasing. So now this is saying that 840 millivolts, and you can see that it's pretty close. Let's go to 128 just to show you that that should give us roughly 2.5 volts. So we are halfway, and you can see that once this catches up, we are roughly at 2.5 volts. So this works nicely, and of course we can decrease the value. And I wrote the code in a way that if you reach the 0, then you cannot decrease towards the negative value. And if you reached 255, you cannot increase above that, so you will not get any weird values here. So you can see that we can feed the required values to the output of this thing. So what I will do is I will wire up everything with this DC-DC converter. I remove these 2 other guys just to decrease the level of confusion. So I will just put this into a circuit. I will fix this USB connection because it reset itself again. And we will see if it works or not, if I burn down anything or not. So I set up the wall system, and hopefully it will be stable for the demonstration of this experiment. So I have random value 63 as the bit, and that is roughly 1.23 volts, and that is read by this multimeter here. So it is connected between the ground here and the output of the digital potentiometer. I also put a capacitor here to smooth the voltage here or remove the noises. I don't know if it helps or not. And don't worry about the cables and everything, because I will put the drawing in on my website as well. Then this guy here is measuring the output voltage of the DC-DC converter here, and now it is measuring 7.9 volts. And the input voltage of this DC-DC converter is now 10.25 volts. In fact, I could measure it. So let's add another meter, and for that I have to replace a few cables, and hopefully I will not mess up the connections. So hopefully this is visible. I cannot put it anywhere, but you can see it's 63 the bit, 1.23, 1.21, so it's pretty much the same, and this should show you 10.25. So 10.24, it's pretty much the same. So now we have 8 volts on the output, and now I start to change the rotary encoder. So we increase the bits here, and that should change the output voltage on this guy here. So as you can see, I increased the bit. That increased the output voltage of the digital potentiometer here, and you can see it here as well, and that decreased the output voltage of the DC-DC converter. So I increase this, let's say, to 128. We are there. So we are roughly at 2.2 volts according to this, and then the output voltage is now 6 volts. So I keep increasing this, and we see what we get. So you see that as I increase the voltage, the output voltage on the digital potentiometer here, which is the feedback signal for the DC-DC converter, then we drop the voltage on the output of this, and you can see that it's relatively stable. So now we are at 3.1 volts, and that went down to 4.1. And as I increase this, then we start to reach the zero value. So now basically we maxed out the output of the digital potentiometer here. So we have 4.7 volts. That's what the STM32 can provide. And then on the output we have some instability, and therefore sometimes I get 0.6 volts, but sometimes maybe just the connections here I get some other values. So it's jumping. But if I go back to some lower value, you can see that we are changing the directions. And you see now that I decrease the output voltage of the digital potentiometer, and then I increase the output voltage of the DC-DC converter. And this happens digitally. So I don't do anything. I could change the voltage by turning this potentiometer. I will show you later how. But basically I'm just doing a digital manipulation, and that's all. And now I successfully reset this because of the poor connection here, so sorry for that. So now at least we zeroed out the output voltage here on the digital potentiometer, so you can see that that's nearly zero value. And then the output voltage on the DC-DC converter is 9.9 volts. So this 9.9 volts is really close to the input voltage, which is 10.25. And of course we have the efficiency and losses, so that's why we have some differences. But you can see that this works. So now again, I start to increase the value, the number of bits. That will increase the output voltage on the digital potentiometer. This is a calculated value. This is the real value measured by the potentiometer, and this will be the output voltage of this DC-DC converter. So I start to rotate the encoder again here. You should see these numbers increasing, and you should see this number decreasing I put something under it so you can see it better, hopefully. Yes, so now it's a very clear number there. So let's increase the things. And you can see that it decreases very, very nicely. So now this shows 4 volts and the potentiometer output shows 3.5 volts, which means that the 5 volt rail is not exactly 5 volt. So that's one thing that you should be aware of, because you have to use it in the formula that is calculating the voltage here. Because why we don't measure it? We have so many analog digital converter inside this unit, right? But there is a big problem. So we are generating 5 volt on the output of this thing, but the internal reference of this AD converter, because this is an STM32, it is 3.3 volts. So you cannot measure anything about 3.3 volts without any kind of manipulation. So if you directly want to measure the output of the digital potentiometer, it might be better to use an Arduino, because the Arduino can measure up to 5 volts. But here we can measure up to 3.3 volts only. Of course, we can build a small voltage divider using 2 known resistors, and then we can measure higher values. And it's actually not a stupid idea, because we have a 12-bit AD converter in the STM32, so we have higher resolution, so we can use larger range and not drop too much resolution as compared to an Arduino. So that's quite doable. But I just don't want to unnecessarily complicate this circuit. It's already somewhat complicated, so let's keep it simple. So we don't want to measure it directly, therefore we have to know the 5 volt voltage very precisely. And again, some advice: sometimes the 5 volt voltage, despite the voltage regulator on board, is different if you are using different voltage sources. So first put your system together, assemble everything, and then turn it on and measure the 5 volts. So you are measuring the 5 volt rail under load. And then when you measure it under load, that should be your number that you use to calculate the voltage output of your circuit, of your digital potentiometer. But let's measure it. So I'm trying to tap, this will probably reset, but I'm trying to touch it gently. So we need a 5 volt and a ground here. And in fact, this thing shows 5.01. So maybe there is something wrong with the formula. We will see it when I show you the source code. But yeah, as you can see here, that 5 volt is not 5 volt. So let's check it here. Yeah, 3.6. So this is measuring correct, because this is also measuring the same. Or both of them are wrong. No, that's not really possible. So just to summarize this before going to the computer, is that you can see that this works well. So I mean, yeah, of course, it's not so good resolution, because this is an 8-bit converter. So if you have a high voltage value that you want to divide, then you get larger and larger steps in between 2 bits. So that can be a problem, but it's still doable. Yeah, this can be actually calibrated, so we can just see how linear is this thing, for example. So what I can do is I can go back to 0, let's say, and then measure the output voltage, and then I go to, let's say, 10, and then I measure the output voltage, and then I go to 20, and then I measure the output voltage, and I do this until I end up on the scale, at the end of the scale, sorry. So I go up to 255, and then I could see what is the bit level, so this number, and what is the output voltage, and how they compare to each other. But that's not so important for me. I just, That's just some curious thing. If you are curious about the linearity of this thing, then you can do it yourself. So this can be your homework. But I just wanted to show you the concept, and I wanted to show you that this works. So once again, just to summarize the things, we have this DC-DC converter, and now we are sort of injecting some current to the voltage controlling potentiometer, and by injecting that extra current or voltage, we are able to manipulate the voltage, which ends up in the feedback of the buck converter or buck controller here on the pin number 8. And since we manipulate that voltage, the buck controller will think that we changed the physical position of the potentiometer, because the values are different now, and therefore it will change the output voltage here. And that's what we measure here. So once again, now I change the digital potentiometer. That will feed a different voltage here through this network of resistors, which will end up in the buck controller, and that will result in a different output voltage. And you can see that it's really stable. So yeah, it's not really jumping, except on the extreme values. I have to figure it out why, but I guess these cables are not so ideal. So if you have a final project, just put everything in a nice PCB. I think it's already a better idea just to have this prototype board and solder everything inside the board, and that will remove the unnecessary noise, because here you are manipulating on a millivolt level, so it might be that this can act as an antenna. I don't know, but might be. So they just pick up some noise, especially here where you are close to the feedback pin, and I don't know how much, but it might be interfering with the things, because now you see that we have like 20 millivolts of fluctuation in the output voltage. So yeah, I rotate the rotary encoder. That will increase the value of the bit, and then through the SPI we send out that integer number to the digital potentiometer, and that will give us a voltage between 0 and 5 volts, and that 0 and 5 volt value, or that value between 0 and 5 volt, will manipulate the DC-DC converter, and that will result in a different output. So that's all, and you can see it works. It's quite nice. So I think this was all for now. I finished with this part, and I go to the computer. I talk about the source code for the STM32. So let's go to the computer and continue the discussion there. So this is the code, and now this code is written for STM32, but I'm using the STM32 Duino, which means that this is basically an Arduino code, but some things are suited or fitted to an STM32, and that is basically the definition of the pins. So when you define the pins, you have to be more careful with the STM32, and if you use the Arduino, you just use pin numbers 3, 4, 5 and so on. But here you have to know it is the port B or port A. And also the STM32 has the I2C and the SPI on different pins than the Arduino. So you have to look it up where you have the above mentioned pins on the Arduino, if you are using it with an Arduino, but otherwise you don't have to modify anything with the code. So we need the SPI library, so that's what you see here. We need the library for the LCD, that's what you see here. We need the chip select pin, that is important for the SPI communication with the digital potentiometer, and I just put this on the PA4 pin. We will calculate the nominal voltage. This was the voltage written on the LCD during the experiment. It's not the precise voltage, but as I mentioned, we cannot really measure voltages above 3.3 volt with an STM32. So I just rather calculate it, because I more or less know the other parameters precisely, so I can calculate it. So this counter 1 is the bit number basically. So this is a number between 0 and 255. So I just write it here. So this is a bit value. Then we need pins, 2 pins, CRK and DT for the rotary encoder. They are placed on the pin B3 and pin B4. For the STM32, it doesn't matter where you put the interrupt pin, or doesn't really matter, because most of the pins can be used as interrupt pins. However, if you are using Arduino, you are more limited with the number of available pins. Namely, you have just 2 pins with the Arduino Uno or Nano. And then a bunch of variables for keeping track of the values of the rotary encoder pins and keeping track of the time. So we go to the setup, we start the serial communication and just print some message just to confirm that it is working. But this is not really necessary if you don't use it with a computer. And of course we need the chip select pin. We tell the software that this is an output, and by default we set it to high. This is a general code for starting up the LCD and just printing some welcome message on it. So we wait for 3 seconds and then we get rid of the message and basically enter the loop after just performing these things. So we read the rotary CRK and rotary DT, so CRK and DT pins, and put those values in a variable. Each of them have their own variables. And then we say that we will use the CRK pin in this interrupt function. And when you rotate the CRK, or when you rotate the rotary encoder and change the value of the CRK, that will trigger the rotate function. And we look for changes. So whether it is going from low to high or high to low, we will start the rotate function and then do something based on that. And we put some time value here in this variable and we start the SPI. And from here, instead of going into the loop, let's check this rotate function. So the rotate function is basically checking the status of the CRK pin upon rotating the rotary encoder, and then it checks what happens when we rotated it. And basically this is just a bunch of different pins that we check, or just 2, so not a bunch. But so we check what is the status of the CRK pin and what was the previous status, and then we enter the code. So we enter this branch, and as you can see, we read the DT pin and we compare it to the CRK pin. So let's say this condition was the condition which happened. So we enter this part of the code and we see if the counter is smaller than 256, so it is maximum 255, then we increase the value. Otherwise, if we already reached the 255, we cannot increase the number more, because that will not lead to any sensible number for the digital potentiometer. So then we stop there and just have an empty code here, so we don't do anything. And if the opposite was valid of this condition here, then we enter this part of the code, and that will cause the decrease of the value of the counter. So we go downwards, but we also restrict that we cannot go below 0, so we can go to 0, and that's all. So this is how we read, and at the end, when everything is fixed here, we just store the last CRK state. And whenever another click occurs in the rotary encoder, then we start from here and go and check how it is related to how the CRK pin's value is related to the DT pin's value. So now we understood what this does here. So let's go to the loop. So we check the time again, and we see if the elapsed time is more than 200 milliseconds. And if it's more than 200 milliseconds, then we print something on the LCD. Otherwise, we skip this part and we don't enter this part, and we just write the current value of the potentiometer on the potentiometer. So if we can enter this function, then we print something on the LCD, and then we update the value of the time now 1 with the millisecond time right now. So therefore we sort of zero out the timer, and then we can count again in the loops. And this is basically a non-blocking coding, so you don't have to delay or wait or anything, because the code will just run endlessly as long as you don't have this condition to be true. Then it enters here, but that is still not really blocking. So let's see what this write potentiometer does. So now the originally high value is changed to low, and then we use the SPI transfer to transfer this 0x11 code, which is basically this set of numbers, and then we transfer the value of the counter, which is an integer number between 0 and 255, and basically that's all. We wait a little bit, and then we also print these values on the serial, and then we go back to high with the CS1 pin. So then we have the nominal value finally. So the counter value is basically the number of the bit between 0 and 255, and that is multiplied by the value of the 5-volt rail. If it's not exactly 5 volt, then modify this value and change it to 4.8, 4.9, 5.2, whatever you have on your 5-volt rail, and just divide it by 256. And you will get the nominal voltage, so we don't measure it. And then the final function which we have to see is the print LCD, and that is very easy. So here we just put the cursor to the 0 point, we write something there, and then we move the cursor after this text. We delete that part, and then we move back with the cursor, because after printing you always put the cursor at the end of the printed message. So it will be here. So if you would start printing the LCD print without having this line here, which puts the cursor back here, then you would go out from the screen and nothing would show up. So cursor first goes here or here, and then the screen is deleted, and then the cursor goes back here or here, and then we just print the number of the counter. And then we go to the second line, and then we print voltage, and then we do the same strategy. So first we clean the screen, so basically let's say the rest of the part of the screen, and then we move back to the origin, and we write the nominal voltage value, which is defined here. And then this is just some formula to calculate the value of the resistors. But this is not used, and you can look it up in the datasheet. So yeah, this was all. So as you could see, it works quite nicely. I will put this in a PCB and put the system together, so I can have a sort of a digital power supply. The resolution is not that good, so I think the potentiometer can provide a better freedom with the voltages, but this works as well, so no worries. I will put the schematics and the drawings on my website. There is nothing difficult about them, so please check them. If you have any questions or suggestions, please leave a comment. So I hope that this video was helpful and you could learn something from this. I think it's quite nice that I could somehow figure this out, because this was a headache for me. So I really hope that there are people out there who can find this helpful. Please don't forget to subscribe to my channel, that helps me a lot. Also visit my website, curiousscientist.tech. You can find all my projects there and a lot of other things which might be helpful for you. So that's all, and see you in the next video.